as we continue to look at what we can do with functions, specifically operations with functions, there's one other operation we can perform with functions that we can't perform with regular numbers. And we call that operation composition. So we can compose functions. Basically, composition of functions is just putting one function into or inside another. So you take one function and make it the input for another function. So when we write this out, to compose functions f and g, if I put one into the other, a lot of times it might look something like this, f and then parentheses g of x. Notice how the entirety of g of x is inside of f of x. And the way I read this is f of g of x. So I'm placing the entire function g into f. Or another notation we could use is I could do f little circle g. It kind of looks like an O with just a small little circle, and then I put the x out there. These mean exactly the same thing. A lot of times people will call this fog, even though it's f of g. So we have two ways to represent f of g of x, where I'm putting g of x inside of f of x. So when I look at this, I always consider the function inside first, and then work my way out. So I'm going to focus here on the inside function being g of x, and then I'm going to look at f of x. So let's look at a couple examples. It's just a little bit different because we don't do this with numbers. When I look at example A here, I have function f and I have function g right there. And when I look at this, this is what I see. I take an 8, plug that into g of x. Then I take that answer and plug that into f of x. Just work inside, out. So my first step is to figure out what g of 8 is going to be. If I plug 8 into the g function, that's 1/2 8 minus 4. So it's looking like I end up getting 1/2 times 8 is 4. 4 minus 4 is 0. So g of 8 is 0. So I can take my original here and rewrite it as f of, and I said g of 8 is 0, so I replace g of 8 with that 0. And then I go through the same process. F of 0 equals, and just plug it into f, the square root of 0 plus 4, which is 2. So f of g of 8 is 2. I'm just working inside, out. Second example. The key to this is realizing I can rewrite him as g of f of 12. So I can work inside, out. First thing I'm going to do is figure out what f of 12 is. So that's going to become the square root of 12 plus 4. So it's looking like my answer is 4, because that's a square root of 16. And then I take that and plug it into the function g. So I have g of that 4. Oh, come on, blue. If I can get blue. There we go. G of 4. And I figure out that's going to be 1/2 of 4 minus 4. So my answer is -2. So I'm just working inside, out. Example C really quickly. I'm going to work inside first, g of -6. So g of -6 is going to be 1/2 times -6 minus 4, which is looking like -3 minus 4, which is -7. So now I take that, plug it into f. So I have f of that -7. Get the right color. There we go. That's going to equal the square root of -7 plus 4. I run into an issue here. I get an imaginary as part of my solution because of the square root of the negative. So I'm just going to say -7 is not in the domain of f of x. And we know his domain is -4 and up if we were to solve that. So there we go, just looking numerically at how I do this. I plug the innermost number into the first function and then work my way toward the outside. If I look down here with two new functions, I have b of x and I have y of x. I need to go through and figure out what b of y of x is. So my first goal is just to say, okay, I'm going to replace y of x with his definition. And by definition, it's x squared minus 4x plus 1. I keep forgetting the last color. There we go. So I replaced y of x with what y of x actually is. So this is saying take this whole value here and plug it into b. So the way I see this is I take that whole chunk right there and he replaces the x. He doesn't go beside him, he replaces the x. So when I look at b of x, this is what I normally see. I see b of x is negative 4 times something plus 2. The difference is I'm now replacing that something instead of with an x squared minus 4x plus 1. So I'm making this function the input. And then from there I can just distribute negative 4x squared plus 16x minus 4 plus 2, and I end up with negative 4x squared plus 16x minus 2. That's my composition of functions. Again, I took all of this and just plugged it in place of that x value. I have another composition here. I'm just actually going the opposite direction. So I'm starting here, and this is going to become y of, and I'm plugging negative 4x plus 2 into the function y. So my function y normally looks like this. Something squared. Oh, I got my colors backwards. Let me erase that really quick. I switched my colors. Y should be y of, there we go, now it's the right thing, negative 4x plus 2. That was going to bug me. So y is normally something squared minus 4 times something plus 1. Before I was just plugging x in, but now I'm plugging in negative 4x plus 2. Negative 4x plus 2. I just have to go through now and simplify, and I have my answer. So if I look at the first piece, I can FOIL that out, knowing the perfect square foiling becomes 16x squared minus 16x plus 4. You could also put them beside each other and FOIL. That's fine. Here, I distribute the negative 4, and I get plus 16x minus 8, and then there's a plus 1 at the end. So if I do all of my combining of like terms, I end up with 16x squared, linear terms go away, minus 3. So there's my composition of functions. Lastly, what looks like Bob is actually b of x. I'm going to put b of x inside of itself. So I'm really looking at b of, his input becomes b of x. Or think of it another way, normally b of x is negative 4 times something plus 2. I'm replacing the something with the whole function b of x, negative 4x plus 2. He's going inside of himself. So that gives me 16x. I get minus 8 from the distribution, plus 2 leaves me at minus 6. So there's just 3 examples of how do I compose functions, putting one function inside of another, or, in the last case, putting that one function inside of itself. Lastly, for this set of notes, we just have a slight preview of calculus, what we end up calling a difference quotient. We're going to start working with these as we go, but I want to go through just one example so that we can start using them in class. I have a function f of x, and I want to find f of x plus h minus f of x all over h. And one of the keys here to realize is h is a constant. In other words, h is not a function. It's just a letter that represents a constant. So we're just going to carry him through like we would any other number. Now when I look at this, I see a couple pieces. I see this first piece right here. That's f of x plus h. I see f of x, and then I just see all the rest of it, which has to do with constants. So over here to the side, I'm just going to write a couple things out. F of x is, we already saw, 5x minus 3. By definition, right there. The f of x plus h, we're going to take f of x and replace every x with x plus h. Or if we want to look at it another way, f of x is 5 times something minus 3. We're just changing that something to x plus h. So it's really 5x plus 5h minus 3. That's f of x plus h. So now when I go through and I look at the structure I have in this whole piece right here, I see a big fraction, it's all over an h, and I'm subtracting something. So now I just pick up the pieces and put them where they go. The red piece, the minus f of x, comes here in my subtraction part. So there's a 5x minus 3 there. Notice I put the parentheses because I'm subtracting the entire function. And then the f of x plus h goes first, so I get 5x plus 5h minus 3. I'm just plugging them in where they go. And now I simplify. So that involves some distribution there. I get 5x plus 5h minus 3, that doesn't change, minus 5x plus 3 all over h. When I look at this, there's a lot of nice things that cancel out, which should always happen with these difference quotients. The 5x's go, the negative 3's go, and I end up with 5h over h. Please don't tell me that that's 4h. I'm not using exponent properties here by subtracting anything. I am reducing, so the h's go away, and I get an answer of just the number 5. Which seems like a simple answer for a complicated process, but this is just our first building block in terms of going towards calculus. So on this page we looked at two things. We looked at this difference quotient here in example 3, and we looked at how do I compose functions? How do I put let me scroll back up, put one function inside another.